All right, welcome back, everyone. So we have our second speaker for the day, Sebastian Bischoff, currently visiting Newcastle from the University of Gießen in Germany for a few months. So if you're keen, you can come to Newcastle and talk to him. And he's talking to us about twin buildings and groups today. Thank you, Sebastian.
Thank you, Stefan, for the introduction. And I would like to thank the organizers for the opportunity to speak here at the Symmetry in Newcastle seminar about twin buildings and groups. And I would like to start with the definition of Coxeter groups, then define what a building is, and then we will ask whether some buildings come from a group. Then twin buildings seems to be generalizations of spherical buildings, so we can ask the same question for these twin buildings. And at the end, we will see that these wall-connected twin buildings are exactly these twin buildings which satisfy this condition. Okay, so in this talk, the pair WS is a Coxeter system of finite rank, which means that the set S is a finite set of elements of order 2 of the group W. And the group W admits this presentation, so it's generated by the elements of S and has the relations, so S times T to the MST is equal to 1, where this MST denotes the order of the product of S times T in the Coxeter group. Yeah, then we have here this length function, which asserts an element to an element in the Coxeter group, a natural number. Yeah, then if we have a subset J of S, then this pair, so the group generated by J and J forms again a Coxeter system. Then we call this Coxeter system WS spherical if the group W is finite. And the Coxeter group, the Coxeter system WS is called irreducible if the underlying Coxeter diagram is connected. And the Coxeter diagram is just has a set of vertices, the elements of S, and two vertices are adjacent by an edge if and only if this MST is at least 3. Okay, then we have the notion of roots. So for each generator S and S, we have a simple root corresponding to S. And this set consists of all elements W in the Coxeter group, such that the length of S times W is strictly longer than the length of W. And we put capital pi to be the set of all these simple roots. Then we have also roots in the Coxeter group, and these are just translates of these simple roots. And by capital phi, we denote the set of all roots. Okay, we call a root positive if it contains the element 1. And otherwise it's called negative if it contains not the element 1. And by capital phi plus, we denote the set of all positive roots. And by capital phi minus, we denote the set of all negative roots. All right. Then for each root alpha, we have an opposite root, which is just the Coxeter group without the root alpha. And we have the notion of prenilpotent roots. So if we have two different roots, then we call them prenilpotent, or we say that the pair alpha beta is a prenilpotent pair if the intersection of alpha with beta is non-empty and the intersection of minus alpha with minus beta is non-empty. And roots are half spaces, which means that for example, if this is alpha, this is beta, then these roots are prenilpotent, or in the second case, one root is contained in the other. So let's say this is alpha and this is beta. So a non-example is, for example, if this is alpha and this root is beta. This is a non-example of prenilpotent roots. Okay, and if we have a prenilpotent pair, then we denote the closed interval of these two roots, alpha and beta, by the set of all roots gamma, such that the intersection of alpha with beta is contained in gamma, and the intersection of minus alpha with minus beta is contained in minus gamma. So for example, let's take blue. So if this is gamma, then this root is contained in the closed interval of alpha and beta. And in this case, a root is between alpha and beta. And clearly, alpha and beta are contained in this closed interval. So we can define the open interval of alpha and beta just as the closed interval without the roots alpha and beta. So now we can start with the definition of a building. So a building has a certain type. So the type is a Coxeter system. And a building is just a tuple consisting of a non-empty set C. And we will call these elements of these sets chambers, and a certain while distance function delta, which maps two elements in the building to an element in the Coxeter group in the following way. So these delta function should satisfy a few axioms. So assume that we have two chambers X and Y, such that the distance of X and Y is equal to W. Then the first axiom is that that W is 1 if and only if the two chambers are equal. The second axiom, the second axiom is that if we have here the chamber X and here the chamber Y, such that the distance is equal to W, and we have a chamber Z, such that the distance from Y to Z is equal to S, where S is in the generating set S, then the distance from X to Z is contained in the set W or WS. And if moreover this S makes the word W from the right longer, then the distance from X to Z is equal to the longer element, so to WS. And we will draw two chambers at distance more far away if the Coxeter element is getting longer. And the third axiom says that, let's draw the situation again, that there exists a chamber Z. So there exists a chamber Z such that the distance from Y to Z is equal to S and the distance from X to Z is equal to WS. And here in the third axiom, there is no assumption on the length of W or WS. So it's just the existence of such a chamber with these properties. Okay. So a first example or an easy example is if we take the Coxeter group, then we can define the function delta, which maps the pair XY to the product X inverse times Y. And then it turns out that the tuple W with the delta function is a building of type WS. So this is kind of an easy example of a building. So we have a building in mind. Then, okay, some comments. By C and delta, I mean that C is just a chamber. Then if we take a subset J of S and a chamber C, so let's say this is C, and we have a subset J of S, then the J residue of C is defined to be the set of all chambers such that the while distance from C to D is generated by the elements in this set J. And okay, a residue is just a J residue of some chamber C. And then an S panel is just an S residue. So if we have if this set J has only one element, then we say it's an S panel. And a panel is just an S panel for some S and S. And we introduce this short notation that PS of C is the S residue or the S panel of the chamber C. Okay, and a building is called thick if any panel contains at least 3 chambers. So we can ask this example of a building, what we have seen, whether this is a thick building. And okay, we can compute it. So let S be an S and W be a chamber. And okay, the distance from W to a chamber V should be generated by this S. And okay, S is an involution, which means that it's either 1 or S. Okay, but this is equal by definition to W inverse times V. And okay, if this is equal to 1, then V is equal to W. And if this is equal to S, then V is equal to WS. So this means that any panel in this building contains exactly 2 chambers for every panel. So it's in particular a non-thick building. And we will see we are mainly interested in thick buildings. So this is not an example which we will consider. Okay, then another comment. If we have a J residue R, then restricting this delta function to the residue R, then it's a building of that type, where J is the type of that residue. And if we say that delta is a spherical building, we mean that the type is a spherical is a spherical Coxeter group, which means that the group W is finite. Okay. Now we should see the first thick example of a building. So take a set, the set X to be the integers 1 up to 6, and we define the set P of all 2 elementary subsets of X, and P will stand for points, and as L we take P1, P2, P3, so these are all points, such that the union of these 3 points is equal to X. So in particular, this union is disjoint. And this L stands for lines. And then we can define the set of chambers C to be the pair of all points and lines, such that the point is on the line L, such that the point P is on the line L. And we define the delta function such that P1, L1 and P2, L2 is equal to S if the points are equal and the lines are different. And we say it's equal to T if the points are different and the lines are equal. And this function can be extended to the whole building. And it turns out that this gives rise to a thick building of type B2. And B2 means just that we have 2 generators, S and T, and that the order of the product of S times T is equal to 4.
So there are 15, this building has 15 points and Q's 2 is 15.
I thought that there are more. So I had something in mind like, is 15 correct?
6 choose 2 is 15.
Okay, then, yeah. Okay, but then we have also the different points. So it's 45, isn't it?
The lines.
So there are, sorry, you mean that there are 15 points?
Yeah,
yeah, exactly. Yeah, sorry.
So you also have a correspondence with perfect matchings in a graph in K6, right? That's P1, P2, P3, P union. So there's probably a connection there somewhere too. Yes, that's what I was thinking. This is some finite geometry that probably Brian would recognize. Yeah.
Okay.
You draw the picture.
Yeah, so you can draw a picture, you can draw this building. Okay, so now the question is there a group theoretical description of a building? And this motivates this definition. So an RGD system of type WS is a tuple consisting of a group G and subgroups U alpha, such that the U alphas are indexed by the set of roots phi. And we call these groups U alpha root groups. And this tuple should satisfy these 5 axioms. And I will not go into detail, but for example, the root groups should be non-trivial. They should satisfy a certain commutator relation, which means that the commutator of U alpha and U beta is contained in the group generated by the U gammas, where gamma is in the open interval of alpha and beta. Then the third axiom states, roughly speaking, that the root groups are conjugates. And okay, the fourth axiom is that the group U minus alpha S is not contained in the group U plus, where U plus is the group of all root groups such that the root corresponds to a positive root. And the last axiom is that if H is the intersection of all the normalizers of the root groups, then the group G is generated by H and the root groups. Okay, and if we have such an RGD system of spherical type, then we can define the set C to be the cosets G mod B, where B is the group H times the group generated by all root groups corresponding to positive roots. And we can define the delta function as here. And then it turns out that, so this chamber set with this delta function is a thick building of spherical type. Okay, now you could ask whether this notion of an RGD systems arise naturally. And for example, if you take, let WS be of type A3 and take G to be the group SL4 of K and define Uij to be the set of all identity matrix plus at position ij, you have an element of the field K, then this tuple is an RGD system of type WS, and the set H, so the intersection of the normalizers of all root groups, is equal to the set of diagonal matrices in SL4 of K. Okay, now the question is any thick irreducible building of spherical type of that form? Okay, so for some RGD system. And therefore, I should tell you what I mean by is it of that form? And this motivates the notion of isometries. So we have two buildings, delta and delta prime, and we have a subset X and a subset X prime. And the mapping F from X to X prime is called isometry if it's a bijection from X to X prime and preserves the Weil distance. And this means if we have two chambers such that the distance is equal to W, then also the distance of the image points should be equal to W. And for a chamber C in delta, we can define the foundation of C as the union of all residues Rj of C, such that J has at most two elements. And again, if we draw the picture in the rank 3 case, then we have three rank 2 residues and three rank 1 residues. And this is then the foundation of the chamber C. Okay. And if we have a building of spherical type, then there exists, because WS is then spherical, then there exists a unique element of maximal length in W, and we denote this by RS. And we have an opposition relation, which means that we call two chambers opposite if the Weil distance between these two chambers is equal to this longest element. And then Jacques Tits proved in 1974 that if delta is a thick irreducible spherical building of type WS, and the rank is at least 3, and we have two chambers C and D, which are opposite, and we have chambers C prime, D prime, which are opposite. And we assume that any isometry from the foundation of E2 of C and D onto the foundation of E2 of C prime and D prime, if such isometries extend to an isometry of the whole building, then there exists an RGD system of spherical type such that the building is isometric to this building coming from the RGD system. So the question is, can we extend such an isometry to an isometry of the whole building? And this is what is known in the literature by the extension theorem for spherical buildings. And this was also proved by Jacques Tits. Namely, take two thick irreducible spherical buildings of rank at least 3, take two chambers C and D and C prime D prime, which are opposite, then any isometry extends to an isometry of the whole twin building. And in particular, this means that if we have a thick irreducible spherical building of type WS and of rank at least 3, then there exists an RGD system such that the building comes from an RGD system. And as a remark, for rank 1 and 2, there exist examples of buildings which do not come from an RGD system. So in this case, this bound on the rank is kind of sharp. Okay. Now, twin buildings are generalizations of spherical buildings, and they were introduced in order to understand RGD systems of non-spherical type. And okay, if we have an RGD system, so in the definition of an RGD system, it was not required that the Coxeter system is spherical. So if we have an RGD system of arbitrary type, then we can define C plus minus as this cosets G mod B plus minus, where B plus minus is the group H times the group generated by either all positive root groups or negative root groups. And we can define the delta function, so either the positive or the negative one, as take G B epsilon and H B epsilon and say that this should be W if and only if the product G inverse times H is in this double coset. And it turns out that delta plus and delta minus are buildings of type WS. And if the type WS is spherical, then these two buildings are isometric. Okay, so now we should introduce twin buildings. So a twin building of type WS is a triple consisting of two buildings of the same type, so delta plus and delta minus, and a certain codistance function delta star, which maps one chamber in the one building and one chamber in the other building to an element in the Coxeter group. And this mapping satisfies the following axioms. So we assume that X is in the one component, Y is in the other component, and the codistance is equal to W. Then the first axiom is that if we swap the coordinates, then we have to inverse the element in the Coxeter group. The second axiom is similar to the second axiom of a building. So let's say here is X, here we have Y, and the distance is W. Then if we have an element Z, such that the distance of Y to Z is equal to S, and if the length of W times S is strictly shorter than the length of W, then the length of X to Z is equal to WS. And for twin buildings, we draw two chambers at distance more far away if the length function is getting smaller. So it's kind of the opposite in the case of a building. And again, the third axiom is that if we are in this situation, X, Y, and W, that there exists a chamber Z such that the distance from Y to Z is equal to S, and the distance from X to Z is equal to WS. And again, in the third axiom, we have no condition about the length of W or WS. It's just the existence of such a chamber. Okay. And we call a twin building thick if both buildings are thick buildings. Okay, so this example motivates why twin buildings are generalizations of spherical buildings. So if we start with a spherical building, then we can define C plus minus as the set of chambers C, and we can define the delta functions, delta plus and delta minus, as follows. So the delta plus function is exactly the delta function of the building, and the delta minus function is the delta function conjugated by the longest element in the Coxeter group. And okay, this RS is an involution, so we can write it as I did it here. Okay, and then it turns out that these two tuples C plus delta plus and C minus delta minus are buildings of type WS, and we can define a codistance function such that if we take the plus component in the first position and the negative component in the second position, then it should be just the delta function times RS. And if we swap the coordinates, it's RS times the delta function. And then it turns out that this triple is a twin building. So this means if we start with a spherical building, we can construct a twin building such that one component of that twin building is the spherical building with which we have started. Okay, and for RGD systems, so take an RGD system, then define delta plus and delta minus as before. And then we can define the codistance function, which maps G B epsilon and H B minus epsilon to W if and only if this product G inverse times H is in this double coset. So we have B epsilon W B minus epsilon. And then it turns out that this triple is a thick twin building of type WS. So if we have an RGD system, we can construct a twin building out of it. And now we can ask the same question: does any thick twin building come from an RGD system? And again, I have to say what I mean with come from. So let's say we have here delta plus, delta minus, delta plus prime, and delta minus prime. And I divide these four buildings by these two lines. And then we have here a subset X of the one twin building and a subset X prime of the other twin building. And an isometry is a map F from X to X prime, such that F is a bijection which preserves the sign, the codistance, and the while distance of the buildings, which means, so it's a bijection between x and x prime. Preserving the sign means that the positive component, so this one, should be mapped to the positive component of the other twin building, and the same for the negative components. And if we take two buildings, two chambers in the one building, such that the distance is equal to W, then the images should also have distance W. So for the positive component and for the negative component. And preserving the codistance means that if we have one chamber in the one component and one chamber in the other component, such that the codistance is equal to W, then also the images should have codistance W. And that's the definition of an isometry. And okay, I should say, as for spherical buildings, we have an opposition relation, which means that we call two chambers opposite if the codistance is equal to 1. And by WS, we say that WS is two spherical if these orders of the products are finite. And then it turned out that if we have a thick, irreducible two spherical twin building, and we have one pair of opposite chambers, C plus and C minus, so these are in different components, and we have another building of opposite pairs, D plus and D minus, also in different components. And as in the spherical case, we assume that any isometry from the foundation of C plus and C minus onto the foundation of D plus and D minus extends to an isometry of the whole twin building. If this is true, then there exists an RGD system D such that that building is isomorphic to the building, the twin building is isomorphic to the twin building coming from the RGD system. And again, the question is, does this assumption always hold, or at least for a few twin buildings? And Titz conjectured in 1992 what is called the extension theorem for twin buildings. So take two twin buildings of two spherical type, take C plus and C minus in the building delta, in the twin building delta, two opposite chambers, and take C plus prime and C minus prime, two opposite chambers in the twin building delta prime. Then any isometry E2 of C plus and C minus onto E2 of C plus prime and C minus prime extends to an isometry of the twin buildings. So this was a conjecture of Titz. And a first attempt to prove this conjecture was made by Bernhard Mühlherr and Mark Ronan. And from now on, we assume that the Coxeter system is two spherical and any twin building is thick of type WS. And okay, they could prove this conjecture of Titz under the additional assumption on the twin building, namely the twin building satisfies condition they proved it for twin buildings satisfying this condition CO. And what does it mean? It means for every chamber C in the one component, the set of chambers which are opposite should be connected. So, okay, let's say here is delta epsilon, here is delta minus epsilon. The codistance is equal to 1. And this codistance is equal to 1. And what does it mean that this set is connected? It's just that we can find chambers which are all opposite. So 1, 1, 1. And the distance in the building is contained in the generating set S. So that's the definition of condition CO. And now Mark Ronan proved in 1995, assume that this twin building satisfies this condition CO, then any isometry from the foundation of C plus and C minus to the foundation of C plus prime and C minus prime extends to an isometry of delta plus and the foundation of C minus, and delta plus prime and the foundation of C minus prime. So it's a first step to extend such an isometry to an isometry of the whole twin building. And in the same year, Bernhard Mühlherr and Mark Ronan proved that the extension theorem holds if the twin building satisfies condition CO. And this means that they extended such an isometry, so from delta plus and the foundation of C minus to delta plus prime and the foundation of C minus prime to an isometry of the whole twin building. And moreover, they proved that a twin building satisfies condition CO if any rank 2 residue satisfies this condition CO. Okay, now you could wonder, because we have defined condition CO for twin buildings and a rank 2 residue in a building is not a twin building, but the definition of condition CO is very similar. So just erase this twin. So a building satisfies condition CO if for any chamber C in delta, the set of all D in delta such that the chamber C and D are opposite is connected. So it's very similar. This is exactly the next remark. So these two conditions CO are different, but they're really similar. Then a rank 2 residue in a twin building, which does not satisfy this condition CO, is associated to one of these 4 groups. So sp4 of 2, g2 of 2, g2 of 3, and 2f4 of 2. Okay, now we could consider a twin building of simply laced type, which means that the product of the order of S times T is either 2 or 3. And then it turns out that no rank 2 residue is associated to one of these 4 groups. So if we have a twin building of simply laced type, then it satisfies condition CO. So for these twin buildings, the extension theorem holds. Okay. Now, if we take a twin building such that any panel contains at least 5 chambers, then again, no rank 2 residue is associated to one of these 4 groups, which means that the twin building also satisfies condition CO. But unfortunately, many affine twin buildings do not satisfy this condition CO. And this is exactly the next step. So the goal is to show the validity of the extension theorem for a larger class of twin buildings, including the class of affine twin buildings. And for this, Bernhard Mühlherr and Anton Chaussot proved independently that any isometry from the foundation of C plus and C minus to the foundation of C plus prime and C minus prime extends to an isometry of delta and the foundation of C minus onto delta plus prime and the foundation of C minus prime. And this is exactly what Mark Ronan proved, except that they make no assumption on the building delta. So the building delta must not satisfy condition CO. So Ronan proved it under the assumption that the building satisfies condition CO, but now the building must not satisfy condition CO. Or doesn't have to satisfy it. Okay, and now we need 2 remarks. The first remark is that if R is so if we take now a building and take a spherical residue R, let's say this is R, then we take 2 panels inside R. So let's say here is P and here is Q. And P is of type S and Q is of type T. Then we call these 2 panels P and Q opposite if there exists a chamber in P and a chamber in Q, such that these 2 chambers are opposite in the residue R, which is a building, so it's defined, and such that the types are conjugated by this longest element in R. So T is equal to RS, S, RS. Okay. And the next remark is that if we take a chamber C, let's say here is C, and we have a residue R, so this residue must not necessarily be spherical, then, I don't know, can you see it? Then there exists a unique chamber, which is called the projection of C onto R, which is closest to this chamber C, which means that closest, if you look at this picture, then the distance from C to this projection is the closest relating to these elements in R. And this means that the while distance is minimal between these 2 chambers by all elements in R. So Alice de Villers, Bernhard Mühlherr, and Hendrik van Maldegem introduced the notion of compatible path. So a sequence of panels is called compatible, let's say this is P0, and here we have Pk. So this sequence is called compatible if the panels Pi and Pi plus 1 are opposite panels in a rank 2 residue. And it turned out that this rank 2 residue is unique with the property that these two panels are opposite in it. So we denote it by R of Pi and Pi plus 1, and such that the projection of this residue is equal, such that if we project P0 on this residue, then it's equal to Pi. So this means if we have here, for example, this residue is R of Pi and Pi plus 1, then if we project P0 on this residue, then it's exactly this residue Pi. Okay, and we will extend the notion of compatible paths to twin buildings. So that's the strategy. Okay, but therefore we need 2 additional remarks. So the first remark is similar in the case of a building. If we have, let's say here, delta plus and delta minus, and we have a chamber C and a spherical residue R. So now it's important that this residue in the other component is spherical. Then there exists a unique chamber in R such that this chamber is closest to the chamber C. And here, by closest, I mean if you look at this picture. This means that, remember, we draw 2 chambers in a twin building at distance more far away if the length function is getting smaller, which means that this distance from C to this projection is maximal with respect to all chambers in R. Okay, and we have opposite panels. So let's say we have here delta plus and delta minus, and then we say that P and Q are called opposite if they contain chambers which are opposite. So P and Q are opposite, and such that the type of Q and P are conjugated by the element let's say this is S and T, and then T should be conjugated by the element of the opposite chambers. C and D. Okay, but this is equal to 1. And this shows that S and T should be equal, so they should have the same type. And in this case, we write P is in Q op, and we mean that the panels P and Q are opposite. And if we have 2 opposite panels, then the mapping from P to Q, which maps P to the projection of P onto Q, is a bijection. So now what is a P-compatible path? So we have P, and we have a compatible path P0, P1, let's say up to Pk. And then this compatible path is called P-compatible if the panels P and P0 are opposite, and if we project P onto the residue R of Pi and Pi plus 1, it should be Pi plus 1. So if, for example, if we project it on the residue R P0, P1, it should be exactly P1. So the panel with a larger index. Okay. Then we define the notion of wall adjacent panels. So take a chamber C and an element S in the generating set. So PS of C in the one component, and take Q1 and Q2 panels in the other component. And then we say that Q1 and Q2 are wall adjacent of type CS if there exists a panel T and PS of C compatible paths from Q1 to T and from Q2 to T, such that they have the same length and the same type. And same length means that here this K is equal to this L, and the type of these rank 2 residues is also the same. So that's the definition of wall adjacent of type CS. And now we can define a graph. So if we have a twin building we can define for each pair CS a graph gamma S of C, such that the vertex set is the set of all panels in the negative, so in delta minus epsilon, such that Q is opposite to the S panel of C. And we define, we draw an edge between Q1 and Q2 if they are wall adjacent of type CS. So in this example, we have PS of C, and we had Q1 and Q2, and here was the panel T. So if this exists, then we draw an edge between Q1 and Q2. Okay, now the twin building satisfies condition WC if the graph gamma S of C is connected for any pair CS of the building. And what Bernhard Müller and I proved is that the extension theorem holds if the twin building satisfies this condition WC. And I would like to give you some ideas of the proof. So it suffices to show that we can extend such an isometry to an isometry of the whole twin building because of the result of Bernhard Müller and Anton Chausson. So take S and S, and P is the S panel of C minus, and P prime is the S panel of C minus prime. And the first thing is that take an element Q, which is opposite to the panel P, and then phi of Q is opposite to P prime. And then we can define the map from Q1 to phi of Q1. Sorry, we can define the map from P to P prime, which maps an element inside P, projected onto Q, then map it via this mapping phi to the other twin building and project it back to P prime. And then it turns out that this mapping is an isometry. And if we take two wall adjacent chambers of that type C minus S, so here's C minus S, then it turns out that these two isometries are equal. And how does it work? So we have here Q2 and here phi of Q2. And since they are wall adjacent, we find a panel T. Now we should take another color. And it turns out that mapping a chamber from here to there, and then to P prime, it's the same as going from here at first to T. So project it onto T, then project it onto Q1, map it onto this panel, project it back, and project it onto P prime. Okay, but using this, then this isometry phi Q is the same as going from here to T, to phi of T, and to T prime. Okay, but this is then the same as going from here in this way. And now I hope that you can see something. So this means that we have shown that this mapping phi Q is independent on the choice of this opposite panel. So these two isometries are equal if they are wall adjacent of that type C minus S. But since delta is wall connected, we obtain a unique isometry from P to P prime. And this isometry extends this isometry phi to an isometry of delta plus and P to delta plus prime and P prime. And using induction, we obtain a map from delta minus onto delta minus prime. And it turns out that this map is an isometry. And now the last step is that if we define the map from delta to delta prime, which maps x either to phi of x, if x is in the positive building, or to phi minus of x, if x is in the negative building, then it's an isometry, and this isometry extends this isometry phi. So the extension theorem holds for twin buildings which are wall connected or satisfying this condition WC. Okay. Then at first we note that condition CO is implies condition WC. So that's good. And what Bernhard Müller and I also proved is that any irreducible three-spherical twin building satisfies condition WC. And the idea is, so any rank 3 residue satisfies a slightly weaker condition than this condition CO. And this weaker condition, together with the assumption that the Coxeter system is irreducible and three-spherical, imply that condition WC holds. And okay, what we have also proved is that all thick affine twin buildings, delta of D, so the twin building comes from an RGD system of rank at least 3, satisfies also condition WC. And the strategy is, if the Coxeter system is affine, then for every generator S and S, the group U plus is generated by all root groups such that the root group is positive and the order of S times the reflection R alpha is finite. But this last condition, so this condition is equivalent with the fact that the twin building delta of D satisfies condition WC. So in fact, if the twin building is affine and of rank at least 3, then it satisfies condition WC. And okay, the last theorem which we proved is that any thick affine twin building of rank at least 3 satisfies condition WC. So not only these twin buildings coming from RGD systems, but all twin buildings. And the idea is it suffices to consider twin buildings of type A2 tilde, B2 tilde, and G2 tilde, because an affine twin building of rank at least 4 is three-spherical and hence satisfies condition WC. So if it's of type A2 tilde, then it satisfies condition CO because it's simply less. So if it's of type B2 tilde or of type G2 tilde, then the twin building either satisfies condition WC or it has the same foundation as the building delta of D, where delta is obtained from the Cas-Moody group of type B2 or of type G2 over the field with 2 elements. And using the previous lemma and the extension theorem for wall-connected twin buildings, and the fact that the condition WC survives under isometries, the claim follows. So we're done. And the conjecture is now that the extension theorem does not hold for general two-spherical thick twin buildings. And yeah, recent studies indicate that there exist 2 twin buildings which are locally isomorphic, which means that there exists an isometry from the foundation and an opposite chamber to the foundation of an opposite chamber, but they're not globally isomorphic, which means that there are some reasons that we can't have an isometry from the twin buildings. And this implies that the twin building does not hold. And this conjecture implies the conjecture that the extension theorem does not hold in general. And the conjecture is that there exist 2 RGD systems DI of compact hyperbolic type, so which means that the type, so it's of rank 3, and this MST is equal to 4, such that the root groups have order 2, and such that there exist 2 roots alpha and beta, such that in the one RGD systems the root groups commute, and in the other RGD systems the root groups does not commute. And okay, the first remark is the construction of such RGD systems. Okay, before that I should say, so I have written down a proof of that conjecture, but in view of the technical details, I would like to pass through the proof a second and a third time before stating this conjecture as a theorem. And the construction of these RGD systems is universal in that sense that we can not only construct 2 RGD systems, but uncountably many. And these 2, the corresponding twin buildings of these RGD systems are locally isomorphic, which means that we find such a local isometry, but not globally. And once this conjecture is proven, we have 2 consequences. The first consequence is that the extension theorem does not hold for general 2 spherical thick twin buildings. And the second consequence is that the Cas-Moody group of that type, so 444 of that type, as I stated before, over the field with 2 elements is not finitely presented. And that's all what I wanted to say. Thank you for your attention.
Thank you, Sebastian. Excellent. Any questions or comments?
I think Jeroen put a link to a picture in the chat. Jeroen and I were having a side conversation about the Sebastian's example early on, where you had 6 points, and he put in a picture of, Jeroen had to go, but he put in a picture of the graph associated to this. We think this is the right thing. That's all.
All right.
Could I ask a question? So is there any,
There she can see you.
yeah. So you've considered affine ones. Is there any chance of this holding for, say, some hyperbolic Kac-Moody twin buildings?
Should go back to the. Probably I can just use these slides. Doesn't work. No, yeah. So the thing is, this conjecture here, once I have proven this conjecture, this means that we have these two RGD systems of compact hyperbolic type, such that the extension theorem can't be true for any hyperbolic RGD systems. And if the root groups have cardinality at least 5, then the extension, if the root groups have cardinality at least 5, then the corresponding twin building satisfies condition CO, and hence the extension theorem holds. So we have to consider RGD systems where the root groups have less than 5 elements.
I see. Okay. Thanks.
Okay.
Any other questions or comments? Online or live? What's hidden under the more button there?
Yeah, can we see what's in the chat?
So that was the chat. Okay, so that's the picture that you posted. All right, well, if there's no further questions or comments, let's thank Sebastian again. And like I said, he's here until April, so feel free to drop in.